Hi guys, I'm Kevin, and I'll admit that I was late to this meetup, but it's not because I don't love you, it's because I underestimated my time. I actually work out of Detroit, but I live in Clarkston, so I don't know if you know what that is, but it's like north of Pontiac, so I'm doing like a big kind of triangle today. So as Brian said, we're going to talk about using JavaScript to wire up the Internet of Things, which is kind of a fascinating topic. I've been working for the past year or so with a group of fellows out of Detroit on a framework called Zetta. I work for a company called Apogee, who has thankfully let me do whatever I want for the last year. And you know, we primarily focus on APIs, and so you'll hear some API-based stuff today as well. How many people were here for Chris's hypermedia talk? Show of hands. That's a pretty good amount. That's a pretty good amount. I was not here, unfortunately. Sorry. I had some work-related thing and other excuses that popped up, so couldn't make it. So Zetta is at zetajs.org, if you want to take a look at it. And we'll go through some of that over the course of the presentation. So, you know, it occurred to me that some people might not be too familiar with what Internet of Things really means. It also occurs to me some days that maybe I'm not so familiar with what Internet of Things means, depending on who you talk to. So I thought maybe I'd start with a brief overview here. So ubiquitous computing. You'll hear this term a lot when IoT is mentioned. Mark Weiser has a pretty good quote here that I'm going to read to you that sums it up. Ubiquitous computing is roughly the opposite of virtual reality. Where virtual reality puts people inside a computer-generated world, ubiquitous computing forces the computer to live out here in the world with people. Right? So you'll see that through Pebble smartwatches, Fitbits, all sorts of wearables that are coming out these days. That gives you kind of a better sense of like living with people. But we've seen this for quite a while. I mean, if we look at you know, control systems that have been around forever, they have this basic notion of a sensor that speaks to a controller and fires off an actuator. If we put this in real terms, I used to work on an assembly line, I'll admit. If you know, a part isn't screwed in properly when it crosses a station on an assembly line, it'll speak to a controller, which fires off an actuator to stop the line, right? And so the whole line stops moving, and everybody looks at you, and everybody gets really grumpy. So IoT is kind of taking this sort of system, this sensor controller actuator model, but applying it to the whole internet, right? So you know, what happens if I stop the line in a plant in Lake Oregon? Building a part for a GM vehicle, right? The main assembly plant also might be delayed because of that, and perhaps they should stop their line, right? And of course, we can expand way beyond that, right? Smart cities is becoming a pretty big topic. You know, smart supply chain management, just goes on and on. You can put smart in front of anything, really, and call it Internet of Things. There's a lot of talk about this right now, too. You'll probably see more talk about Internet of Things than like real life stuff happening. It's because Cisco has this really big hype machine out there, right? And they're calling it Internet of Everything. Everyone has kind of their own brand for it. But you know, the Cisco-based report, you know, keep in mind Cisco wants to sell you hardware to make this happen, estimates over 50 billion connected devices by 2020. And of course, this sort of thing makes other companies say, hey, I've kind of been doing something like this for a very long time. Let me attach IoT to my name as well, right? So buzzwords are important. IoT is our buzzword for tonight. Of course, it's not without its problems, right? If you start getting into this, maybe you guys have played around with node bots, which is a really cool thing. I know Brian does a lot with that. But really what you're focused on is something that's running locally, right? You know, I've got my laptop connected to this Arduino. We're doing really cool things together. It's magic. But what happens when you need to expand beyond that little scope, right? You have to go across multiple locations, potentially. What technology do you pick? There are many. You know, MQTT is becoming more popular these days for IoT-specific things. It's kind of a lightweight pub/sub model. If you look around, a lot of vendors are basically doing massively distributed pub/sub on top of this. Which I don't know if you guys have like enterprise experience doing like pub/sub architecture, but that kind of scares me a little bit, doing internet scale. Question?
Two guys on the left are technology, one on the right
It's all the same to me. This is also the coordination aspect that I talked about, right? Not just communication, but how do we wire up interactions, intelligent interactions between devices? Maybe we don't even know everything up front, right? But we need kind of an adaptable model. As we get more information over time, that might change the kind of interactions I have. Has anyone heard of big data? So, a lot of big data people are going crazy over IoT right now because IoT produces massive amounts of data. If you've got a sensor, 3 sensors, 6 sensors on every street corner, that's quite a bit, especially in Ann Arbor. And this is something that a lot of folks don't really focus on right now, but something that we focus on a lot is experience. How does it feel to actually interact with this system? How does it feel to be a developer working with this system? Does it feel normal? Does it feel comfortable? And of course, we hope that Zetta does. So I'm going to go through some decisions that we made, go through the architecture a little bit of Zetta, and then get into some actual coding so you guys can see the JavaScript and we can talk about that. Also, I don't know if it's cool with the organizers here, but if you want to ask questions as I go along, feel free to do that as well. So in terms of picking technologies, we had a lot of options. But we did decide to go with HTTP, not just because I work for an API company, but because we actually believe APIs are a great thing. When I say APIs, I mean web APIs here. So, and then we layer on some WebSockets for streaming. And we also use Speedy. Some of you have probably not heard of Speedy. It was a Google-based protocol that they were trying to replace HTTP, right? HTTP has a bunch of different problems with it, though it is vastly successful. And Speedy has a bunch of improvements to HTTP. That eventually made its way into HTTP 2, which was recently finalized. So, in the future, of course, we're going to look at how we incorporate more HTTP 2 stuff into Zetta. One important thing that I mentioned is crossing these network boundaries. So just a couple of features that we require there. Access. If I've got a server running in my home, how do I access that from my mobile device when I'm 3 towns away, when I'm across the world? Interactions. Again, how do I have device interactions happen, even possibly when I'm not involved as a human being? And then the streaming component is also pretty important, right? We need a low latency way to get sensor data. I know this is a JavaScript group, so you guys are probably familiar with Node. Even if you don't do any kind of Node development, a lot of the tooling around front-end development is moving over to Node, so I'm sure you have some experience with that. So I probably don't have to convince you too much on why we chose Node for our platform. But Node, as you know, is evented, it's async. It turns out the device world is this way too. A lot of times they spit out an event. A lot of times if you send it a command, you're not going to know if it received it right away. It's going to take a while. So Node's programming model fit really well on top of that. It's open source, and we really love open source. We do a lot with open source. In fact, I'd probably say 98% of what my team does right now is in open source, which is kind of cool. And it's cross-platform. I'm not sure this is as important to everybody else on my team, but I spend a lot of time on Windows, and I know that a lot of other people are using Windows. And so having something that's cross-platform from the get-go was pretty important. And therefore, we make sure Zetta is cross-platform. So, a big reason is because JavaScript. Right? A lot of people have stayed away from this embedded programming world because there's a big wall there, right? If you've ever been in a room with a bunch of embedded C developers, a couple of things are going to happen. Either they're going to make you feel really stupid and you accept that you're stupid, or they're going to make you feel really stupid and you accept that they're assholes. But either one is not really good. But JavaScript is known pretty well by almost every developer I talk to. Even if it's misused in the browser, there tends to be 1 or 2 or 3 ways to do it in Node, and people seem to be a lot more comfortable with that. So now I'll start talking about the architecture a little bit. some of the internal workings, explain how Zetta really works. It'll make the code a little bit easier to understand, know a little bit more of what's going on. So this might be a good diagram to point to. So Zetta can run as a hub on your private network, right? Or multiple hubs. Multiple devices can connect to a single Zetta hub. Zetta will expose an API over those devices for you. Zetta can also talk to other Zetas. So it can peer with another Zetta on your private network, which may also have its list of devices. And all the APIs can be exposed locally as well. So clients, your mobile phone, whatever it might be, can speak locally to these Zetta instances, right? So that means it runs even when the internet's down, which is kind of a cool thing. It can also do this peering with something that's in a data center. Maybe it's running on Heroku. Maybe it's running on Azure. This works on Bluemix as well, if anybody uses that platform. And of course, we can have clients in the internet coming down here. Now, the cool thing that I think maybe this diagram doesn't really convey very well is this works because we are doing a WebSocket call going outward. So think about this running in Heroku, right? This Zetta hub makes an outbound WebSocket call, which then gets upgraded, and we kind of hijack the sockets at that point and start using a speedy protocol, which can multiplex HTTP requests. And so now we can proxy requests coming into this guy all the way down to your private network. So this kind of allows us to cross network boundaries. And this doesn't have to be from a private network to something public, but it can also be within your own organization. So when designing the API, we had a few different architectural properties out there. Decoupling of implementations is pretty important because your Zetta client may be vastly outdated from your Zetta server. You should be allowed to iterate on that server as much as possible. And that last part, the iterating part, is independent evolution. It needs to be able to do that. So we need scale, of course. We're talking about the internet, right? We're talking about tons of devices connecting up. Load balancing is really important. WebSocket load balancing, as it turns out, can be a little tricky, but the HTTP stuff is very well known. Of course, this is something, if anyone ever got into XMPP really got this one right. To centralize complexity and distribute simplicity, they always had this idea that let's take all the complexity and put it on the server. That way we push simplicity out to the clients. And if we have an explosion of clients, then our ecosystem grows, and it's a positive thing. And that turned out to be the case. So. Of course, we want to reduce latency, right? I mean, if you've ever made any application that was connected to the internet or a network at all for any customer, they always complain that it's slow, even if it's as fast as you can go, right? And then they complain that it's not blue enough or something. And we need to support event streams, of course, temperature data, barometers, all sorts of things. So we take all of these desired architectural properties and we try to map them over to architectural constraints. And we get things like client-server, stateless, cacheable, layered system, uniform interface, et cetera, which is essentially just REST, right? I don't imagine most people have read Roy T. Fielding's dissertation on REST, but he talks about this pattern in architecture of coming up with a desired set of properties and then some constraints that satisfy those properties and then listing the trade-offs, right? The paper, in large, talks about this architectural model. And so if you were at Chris's talk about hypermedia, you might know a thing or two about hypermedia, and that's awesome. We happen to use it. And the format we use is called Siren. As a brief overview of hypermedia, it is essentially, if you think of a hypermedia API, it is an API that's going to provide you links to what you can do next. If you think of the Google search page, right? You're presented with a form that you can fill out and do a search, right? So you go there, you type in sem.js, and you hit search. You're presented with a bunch of links, right? And you can go down those links and you can select which one you want. Hopefully it's to this meetup. Hypermedia APIs work just like that. There are different formats, and they don't all support the same things. Siren happens to support that form style, which it calls actions, and of course, links as well. So we get kind of all of that by borrowing REST and by using hypermedia, except for event streams. I haven't seen anyone kind of mixing these two yet. So here are a couple of ways that event streams or streams of data are done today over HTTP. We've got webhooks, chunked transfer encoding. So the response will send like a little bit of a response and then say, hey, there's more coming, and then send a little bit of a response until it ends. There's HTTP pipelining, so you can send multiple requests over the same socket, but that kind of has its own problems too. Lawn polling is really a little too much high latency for us in our use cases. Imagine if a sensor is spitting off data every 10 milliseconds or something like that. The HTTP request for lawn polling is going to take up all of that again, right? There are server-sent events, which is kind of a really cool technology. It wasn't adopted by every browser vendor, unfortunately, so we like to say that we want the browser to be a primary consumer of our API. And if it can't be, then that's a problem, right? So webhooks, reason I don't like them for this use case is it requires a whole registration step. You've got to have plugins deep into your system, especially when everything's varied as it is in Zetta. And you'll see Zetta lets you model your own devices, so that makes it kind of difficult as a platform to allow that. Certainly, there could be an extension on top. Chunk transfer encoding doesn't work in every browser. In fact, I think most browsers will block the entire thing until it has the full response. So it completely kills our need for streaming. HTTP pipelining introduces something called head-of-line blocking. It can't respond to, it has to respond to request in order. So if it sends one request that takes 200 milliseconds and the second request would only take 10, the second request still has to wait for a response until the first one's done. And HTTP2 and Speedy try to fix that quite a bit. It's a big problem and why a lot of people haven't adopted pipelining. We talked about lawn polling not working, and we talked about server-sent events having its issues cross-browser. Although it is a pretty cool technology if you haven't looked into it. It's very simple. So this is what we do. We just upgrade to WebSockets. It would be nice if we could support everything over HTTP and not have to push WebSockets on folks. But it turns out WebSockets does a lot for us. So, and you'll see how those WebSocket links get presented in the hypermedia responses too. So we're actually using hypermedia plus this WebSocket event stream. One of the benefits of that is you don't have to know a URL up front for that WebSocket, right? If you were using another technology, some ESB MQ type technology, you would need to know like topics or queue names and things like that. You could technically use that sort of style with this style of hypermedia, but the benefit on the client would be they wouldn't have to know all those names up front. You could change them on the server side if you needed to, things like that. So here's some of the components of Zetta. You have Zetta running as a process. It's actually a library. Think of Express, how you can get Express, right? And then you wire things up to it, and then you say, hey, I want to listen. Zetta works similarly. When you do that, you can wire up 3 separate things. One is Scouts. Scouts find devices on the network. So if you're looking for Bluetooth, for instance, it'll look over Bluetooth. If you're looking for to see if there's a Q hub connected to that network, it'll do that. And luckily, Node has tons of libraries out there for hardware already. So for the most part, we don't really have to focus on some of those lower level details. Scouts create drivers. Driver is going to be that representation that you interact with inside of JavaScript. And it's also going to model the API response as well. We have a concept of apps that can run on the platform as well. And apps can observe different devices coming online and then wire up interactions between them. And we'll see some of that as well. We also used the app model to wire in certain extensions to the platform. Haven't figured out how to differentiate that yet, but it turns out that we can access just about anything internally to Zetta by going through an app. And you can think of things, extensions. Good extensions would be like adding authorization to calls, adding compression if it doesn't exist, all this sort of thing. Here's a quick look at what that model is going to look like. We model all of our devices as state machines. Now, some devices don't have state, and that's OK. Think of it just a simple sensor spitting out data, right? Not really a whole lot of state you want to model. But something like an LED certainly does. So this is, if you've ever seen, like, here's a simple example state machine. It was probably like an on-off switch. That's essentially what an LED is. So we have to define a type for it. We have to define an initial state. And then we have to wire up transitions. We say when the current state is off, we want to allow the turn on transition, and vice versa. When it's on, we want to allow turn off. And then we map those things to functions that can actually run the logic. And we'll see this more when we go through the code. As I stated earlier, those transitions are actually modeled through the API. So in this case, it'll be an action on that device that says turn on. The necessary fields you need are there. href, method, it ends up looking a lot like an HTML form. And the cool thing about depending on the state machine model is that when the only available action is turn off, for instance, that is the only available action that will show in the HTTP response. So here we talked about consuming event streams. We have this notion of an object stream. So we'll get a JSON object back with it. The href, you don't really have to know what that is, what the value is. But it's going to start with the WS, in this case, for WebSockets. And it might be a little hard for you to see, but what comes back is a topic. So in this example, it's heartbeat/1/pulse. We're listening to like a pulse event stream. A timestamp comes back with that, and a data value. Right? In this case, it's 61, 65, 69. It's numeric. One cool side effect of this that we found is you can actually monitor an entire resource and say, when a transition does happen to you, I want to get a notification of that, right? So if the LED turns on, send me a turn on notification. If it turns off, send me a turn off notification. I want to know that these things are happening to the device. And that looks sort of like this. Again, might be a little hard to see. Well, maybe we can pull it up in the browser later. We also have the concept of binary data. For that, it's advisable to put some kind of type on there of what's going to be returned. Otherwise, it's just going to be total gobbledygook. In this case, it's video MPEG, and it's just a stream of my face. So one cool thing about having this style is that you can build up reactive clients. If you're not familiar with reactive programming basically says, I want to wait for something to happen, and when it does happen, let me know. Right? We could do a whole other hour on, on reactive programming, I think. So this is using a Siren library. By the way, I'm the initial author of Siren, but there has been community contribution since, which is, again, the hypermedia type, and this library as well. So this is a node library that lets you interact with Siren APIs. So you can load a root URL. You can look for a specific link that is identified by peer with the title Detroit. You can filter the list that comes back to I want something that has a property type of sound. Then I want to follow a link to get the sound level, right, which is going to be a WebSocket link. Monitor that and subscribe. Right. This actually does work. Actually, I think this exact code sample will work because that's a live URL. And then I just put kind of a simple wrapper around that for Zetta on top of Siren, right? And so this kind of stuff becomes really simple to look at. And if you think about modeling like mobile apps on top of this, right, you can have a very responsive mobile app that tells you what's going on as it's happening. We've done a couple of things towards that, but we've seen other folks in the community do kind of cooler things with it, actually have whole demos set up, and it's kind of nice. All right, so it's time for a little code demo. It's been a little while since I've been in this code, so let me. as my coworkers were telling me earlier, they were like, Kevin, it's been a while, hasn't it? This is a really obvious bug. Where am I? Nope. Make a new directory. Cool. Is that font big enough? I have a hard time seeing anything, so. Is that good? Okay, great. Where am I? Great. So first thing we're going to do is install Zetta. And we're going to install Zetta-device, which we use to make device drivers. Do that. Great. So we should have a node modules directory there. And let me fire up a server.js. And we'll see if this color scheme works for you guys. So we'll do var Zetta equals require Zetta. And we can do Zetta.listen 3000. OK, so this isn't going to do much, but it should run. Let's do one more thing. Let's give it a name. Great. So this is usually like my no tricks up my sleeve. This is just an API. It's a JSON-based API. We can see there's not a whole lot here at the time. Links, SEM.js, if we hit that. Once we start wiring up devices, we'll start to see some devices appear here. This is kind of the route as it exists today, currently. All right, so we are going to do a mock photocell. I've seen people use like live devices when trying to demonstrate this, and all the problems that happen on like the live device side and all those protocols tend to kill demos. And I feel like you already have enough working against you in a demo. So we will look at something that's running in my office right now, assuming that the camera is working. So. For wiring up devices, we're going to do a mock photocell that just has a single stream, just so we can see what that looks like. We do use an inheritance model, and it wasn't an easy decision. But if we start wiring that up, of course, and if you've done this, you got to do something like a device.call this. This is something I think I've seen a lot more in Node than I've seen in the browser side, probably with good reason. And we'll also put a property on this guy called intensity. Do the old inheritance call, which is not a virtue in the browser for a lot of folks. And every device driver in Zetta is going to have this init function that gets called. It gets passed a config object. And again, on the config, we have to set the type, photocell. We'll set a name in this case, photocell 0. And we'll monitor this intensity property. Now, at this point, if you were doing just a bare device driver like this is, you would probably wire up some connections to whatever physical device it actually is. A lot of times, you end up using a Scout model, which generates these device drivers for you. So, but since we're doing a mock driver, I will have to remember some math, and we'll try to make a sine wave. Just a quick set interval. And I need, who has never done var self equals this? And so we do self.intensity equals math.sine counter times math.pi. I think that's what I want. OK. There are a couple of different ways to do a stream, but what we've found usually is that we want some kind of property on it that we can access that updates frequently. So .monitor gives us kind of a shortcut into doing that. We'll require the photo cell. And then we'll just do a .use photo cell. Let's see if this guy runs. I'll clear it first so it's not so low. OK. And if you could see those logs, you'll see that it picked up a new device called PhotoCell back in our API. You'll see we have this new device here, right? And if we click into the self link for PhotoCell and scroll down, you'll see we have a link here that has a title of intensity and an href that we can subscribe to. So WSCat is a utility that you can get with Node if you do an npm install -g. It recently moved out of the WS module, which has like a WebSocket server and a client you can use. And I think it's in its own module now called WSCat. It took me a while to figure out. So we'll subscribe to this guy. And because I put a very low 100 millisecond refresh rate on that, you'll see this streaming in pretty fast. Again, in that topic timestamp data. There we go. And so I'll take a little aside right now and say we do have a better way of visualizing this stuff usually. This is called the Zetta browser. This is, again, free. There's a GitHub repo out there, but usually I just use browser.zettajs.io. And this is essentially just an API client on top of any Zetta API. We'll run that and check this out. And we can see that photo cell there, and it's actually visualizing the data. It's doing a little bit of trickery here and saying, is the data coming back, is it numerical or is it categorical? In this case, we know it's numerical, and we render it on a graph. I guess my math wasn't too bad. That doesn't look too bad. So, OK, another thing I want to show you guys is, I know we kind of saw it already, but I want to show you actually modeling those state machines and what that looks like. I think that's a really important part of Zetta. And we'll do an LED because, again, it's easy. Do our requires there. Then our boilerplate. And then remember, we need that init function, like it's passed a config. And this is where the magic sort of happens with the state machine stuff. So again, we'll do a config type LED, and we'll say name lamp or something like that. An initial state of off. And this can be set dynamically by the Scout when it finds a driver. But again, in this case, we're just doing sort of a bare driver. And then we have our transition model, right? So we'll say when the state is on, we want to allow the transition turn off. And again, we'll just swap it around for when the state is off. And then we have to do a simple mapping. We'll say the transition turn on maps to this dot turn on, and turn off maps to this dot turn off. And so we'll make those functions now pretty easy. Turn on equals function. All of this is async, so we pass a callback in. Equals on. Trying to go fast so you guys don't have to spend too much time watching me type. And turn off. Any questions on this? Sometimes I get a few. That is not a JavaScript map function. That could be confusing. Yeah, that we're not changing the contents of an array and returning them. We're mapping the label turn on to a specific transition handler. I'm sorry, I couldn't see what that was. Kind of a light right here. Hopefully I was looking in close to the right direction. So we'll require this guy again. What's the question?
Do you allow self-transitions?
Self-transitions? What do you mean by that?
Like in a state machine, you want to transition from one state to another state or transition to the same state?
Yes, you could transition to the same state. Yeah. A lot of times when we build out state machines like that, we end up finding, if they're simple state machines anyway, we end up finding that there is only ever one state and one transition, transitioning back to itself. And a lot of times we'll just remove the state machine logic altogether because it's just the default run state. All right, so we wired that guy up. Hopefully I got all that right. We'll try to run it again. Great. We'll see that an LED was also discovered. If we come back here and refresh this guy, we have our lamp. We'll build it up a little bit. Again, our photo cell is running, and here's our lamp. We can turn that on. We can turn that off. And again, this is all API powered. If we go into the lamp directly, we'll see the raw API response. And again, here's the HTTP requests. The accept here is application/vnd.siren+json. That, of course, is the media type that we're using that's represented here in the response. And if we come down here, we can see that there's one action available, and it's to turn that LED on. So, all right. So I mentioned three things on that diagram of what you might have to code while using Zetta. It was a Scout, a device driver, which we've been looking at, and an app. I'm not going to get into Scouts right now because it can get a little hairy, and it doesn't make as much sense when you're doing mock devices anyway, right? So there's really nothing to find out there. So we're going to do an app. Photocell is producing a value. LED has a state. Is it on or off? We're going to wire up just a simple app that's running here that says if the value of the photocell is above a certain value, then we want to turn the lamp on. Otherwise, we want to turn it off. Pretty simple. But we'll give you a little view into what those apps look like in that reactive model that we discussed. And this is a little simpler. You just export a function that takes an instance of the Zetta server. And this is what I mentioned. We can wire up a lot of extensions this way. Just turned out to be pretty handy. So there is a query model that sits on top of this. It can get pretty complex. You can do SQL-like statements, not in the Mongo type way where you're building up giant JSON objects that represent what could be more concisely represented as a string. You can actually use strings. It's something called Calypso Query Language. We've developed a lot of the stuff that is running as a dependency of Zetta in-house. And of course, it's all open source. This is one of those technologies. We're not going to look at that right here, but we'll look at it in the browser. What we want to do is come up with a photocell query. And we say server where type photocell. We can do really basic queries this way using this object syntax. But when things get complicated, which they often do, or I should say complex, using that string model is a little bit easier. We also want an LED query. And then we'll do a server.observe, and we can observe on multiple. So we'll observe the LED query and the photocell query. I'll explain this in just a minute here. So what this is doing is saying whenever an LED comes online, or whenever something of type LED comes online, and something of type photocell comes online, I want to fire off this callback function here, right? And that'll keep happening in pairs. So if you have, a second LED come online and then a second photocell come online, this function will pair them and get called as well. There are a bunch of other functions we can do on top of this, different reactive combinators we could use, but this is just kind of the simple example. So the streams that we're able to subscribe to over the API, we can also access internally in the platform. So we'll do var stream equals photocell dot create read stream intensity. And this will get us that stream back. If we do a stream on data, we get that message, and it's the exact message that we looked at over the API. And so we could say if message.value is greater than 0.5, and the LED has what am I doing? Available turn on transition. I want to call turn on the LED. And then we'll do the opposite. Message.value is less than 0.5, and LED has the available transition turn off. LED.call turn off. Any questions on this before we see it in action? Yes?
You said when it comes across a device that has an LED and a photocell, that will run
Two separate devices. So yeah, when one device comes online that identifies itself as an LED, and then a second one comes online that identifies itself as a photocell, then this function will be called.
Can you hint at specific devices at all, though? If this one device comes on and that specific device?
Yes, you have to know how it is specifically identified, though. And sometimes that'll come through your Scout as well. The Scout knows that I'm using Bluetooth, and there's this certain attribute associated with that protocol, and I know I can identify this specific device as being something, right? And then your query can get a little bit more complicated, right? You can say either where like name equals this, or you can say where location equals bedroom, and or location equals bathroom, or something like that. Keep tacking it on.
Do you support any temporal operator where you check for events happening within a span of time or certain number of events?
We don't have any built-in temporal things. I don't imagine it'd be too difficult to build that on top of this, though. So just being able to plug into that event stream here means that you could start monitoring those over time. One issue with that potentially is the amount of space you're taking up, right, in memory or on disk, wherever you're spooling this. And when we run hubs for demos and examples, typically they're a BeagleBone Black, which is a really small machine, or a Raspberry Pi, which is kind of small, and we have limited resources available on that. So, and that's true for in the home as well. If you're doing like a hobby project, you'd probably use something like one of those, small computers. Or if it's like a production run, you're a big company, you're rolling something out. You want to get that hub as cheap as possible because you're probably going to be deploying plenty of them. And so that hasn't been a use case yet, but that's certainly something we could model on top. And it could certainly work for something that's for a Zeta running in the cloud, because it's the same code base running locally on the hub and in the cloud. So, is there another question over here somewhere?
I've got one for you.
Okay.
Now, can the client act as a subscriber? Like, let's say the client was a smart client,
Mm-hmm.
and
Client meaning like a mobile app or something like that?
A device.
A device, okay.
The device you're listening to here,
Mm-hmm.
if it can respond to actual commands like turn off or reconfigure,
Mm-hmm.
are there APIs in there that actually allow you to do that?
You'd have to kind of model those yourself in the device driver. Like we looked at the LED, modeled those kind of states. There are cases where that state on the back end is dynamic and kind of told to you by that device. And so you have to work with your scouts and your drivers to get that code working like that. Yeah, but it's certainly possible. Yeah.
Yeah, I'd like if I had a refrigerator that was smart, and there was like a software upgrade, I'd like it to listen and subscribe to something coming down to it.
Oh, I see what you're saying. Yeah.
Repair itself, like an elevator, anything that is smart enough to not only be observable, can it actually act as a subscriber to whatever's controlling it.
Yeah, sure. And we don't. I don't have access to that code, but somebody who is using Zeta is doing that for their entire hub, actually. So you can make an API call that updates the hardware on the hub, or the software, the OS on the hub itself. And so that's kind of a similar thing, right? If it's your fridge, if it's something. Yeah, that would be cool, but totally possible.
So another question I've got is, all these things that are being observed, can we create classes? Like, let's say I've got a smart device like an elevator,
Mm-hmm.
and doors jammed. I want to shut it off right then and there. Are there different elevations in terms of this thing that's observable?
So you don't care what the current state says. You want to force a command through. Is that right?
I wanna find out if those doors are jamming on that elevator
Mhm.
right then and there. I don't wanna wait till it observes a bunch of devices, 100 elevators. I wanna
Sure.
find out that one is jammed right now. I want it
Sure.
off.
Well, if the elevator knows it's jammed, it can certainly send out a signal and transition into a jammed state, right? Or if that's something that you have to wire up in logic to say, you know, I realize it hasn't responded in 10 minutes, I'm going to put it into some error state, you can wire that logic up in your device driver as well. Is there a question in the back? Someone thought I saw a hand. Okay.
I have a question.
Yep.
So if you have an ecosystem with several micro devices that you're listening to,
Mhm.
and say you have certain macro devices that need to do something more meaningful with data, do you have any way of kind of API filtering where the macro device has got more intelligence and do more operations than a micro device?
Yeah, so we've done something like build up a composition of devices. So say you've got multiple devices coming online, but then you want kind of a bigger logic device to control all of those. In the Scout, you can actually use that observe function to wait for all of those devices to come online, and then you can provision your macro device with a reference to all those other devices. So it then has control over all the sub-devices. And I have an example of that I can show you later if you remind me. All right, let's move on. So again, this app is going to listen to the value of the photo sensor and change the state of the LED. We need to wire this up. Hopefully I got all that right. Great. Oh. Let's see here. Not sure that's wired up appropriately. Let's see. Intensity, great. LED, photocell, great. The LED doesn't have a stream. It doesn't stream any data. It just has a current state. That's weird. Where are my coworkers in the audience? Anybody see an error?
What's not functioning?
What's that?
I'm unaware of how it was failing.
I don't see any errors. What are
Yeah, I don't see any errors either. I don't know. It's just not working.
Were you expecting the LED to turn on when?
Yes.
When then I think you're
Yeah.
greater than less than backwards.
Is it backwards? Yeah, we'll do a little JavaScript debugging right here.
You will tell me.
Ah. Where's my well actually guy in the audience? What's that? I think I heard Adam. Was that Adam? Message.data. Thank you. I'm glad you came along, Adam. Appreciate it. There we go. Ta-da. And so what I'm not showing you here is that you could wire up these interactions across different servers. Let me show you a different Zetta API that's running right now. It's running on Heroku. And so this represents a setup that we have in our office in Detroit. Let's check the drop cam. If you ever use Dropcam for latencies, or for demos, know that it has a lot of latency associated with it. Whenever we do a demo and kind of show this, a lot of people are like, oh, yay, it finally happened. We're like, no, it happened like 5 seconds ago, I swear. So this is an example of the query language that we have. So we'll say where type equals arm, and it'll filter this. And this is actually going over the API too. So we get the API link here. If we were to open that, we see that we actually get a response that knows the query is where type equals arm, and our response coming back has our robot arm there. So, right. So this is our robot arm. Let me shrink this down a little bit. We'll move it, and we'll eventually see it move. Do that a couple of times. There we go. Oh, it looks real shaky right now, doesn't it? That's almost like a cool robotic effect to it. That's awesome. Yeah, so we got that. That's kind of fun to play with, and you know, this is totally public and open, so you can come scare us in our office whenever you want. It happens all the time. Lots of people are doing demos on this, and you know, just every now and then I'm here, I'm like, ah. You know what? I tried for a really long time to get it to pick up something, and then I left it there for days because I was very excited it had something in its claw. Oh, here's the display screen. So it's probably hard to see, but there's a little display screen right here. This is an example of connecting kind of an action change to change the message to a stream. So we should see a new message coming out of this.
Flip the video to the other side away from the light.
Oh, yeah. Oh, the UI didn't change. Sometimes that happens. So it says hello SemJS there, and we'll see that come in here. I don't know why this is finicky sometimes. Oh, there we go. So you see the stream come across. So we talked about how the browser represents categorical versus numerical data. It just does some function on those to come up with some kind of color and spins them through. So this is, this guy, there's a BeagleBone black running in the background there underneath the Philips Hue bulb. We have a couple of Arduinos running that are connected to sensors. So we have barometer coming through. There's also a photo sensor in here, humidity, so we get those values streaming, sound, temperature. They're really cheap sensors, so they're probably not totally accurate and they haven't been calibrated, but it works to show streams. So computer's getting kind of hot. That happens with the Zetta browser. So that guy's running in Detroit. We've got, you notice this is pointing to Heroku. Let me go back here. Anyway, you'll see it up here. This is pointing to Heroku, right? So this is pointing to something that's public. The BeagleBone there is making an outbound connection over HTTPS to our Heroku, forming that connection, establishing that speedy protocol that we talked about, and it's proxying connections back down to what's running in the office. Can you reprogram the ARM from like afar? Yeah. In this case, you'd have to be pretty good to figure out how to do that. The ARM, it's like a $50 cheap toy ARM, honestly. So there's not a whole lot of programming in there. I think we're doing a UDP from the BeagleBone to an Arduino that is then controlling the ARM. So.
You should tell them that it's doable.
What's that?
I said you should have told them that it's doable. You get into work tomorrow and it's going to be like,
You'll probably see it right now.
Someone recently came into our office and they were shocked because they thought this robot arm was like massive and like the whole setup was really big. The robot arm was like that big. It's like tiny. Does it have a what? The robot arm is a cheap piece of crap, just to be honest, and the thing will break occasionally, and we'll hear now we know somebody's trying to demo it, but like is testing the limits. Like, let's take the arm back all the way and see what happens. All right, so you know what? We're linking up to this ZettaCloud2.herokuapp.com. This is unscripted, but why don't we show what that looks like? There are a couple of ways you can peer with another Zetta server. Just doing a .link here is one of them. So when we do this, we should see SemJS pop up from Heroku as well. Okay, we'll see peer connection established here in the output. And if we come back here, there's SemJS. Detroit takes a little bit longer to load because there's more in there. But if we come down here, we can see now that we are accessing something that's public, that's running on my laptop right now. So, and this, one reason I did this is to demonstrate that the Zeta that we're connecting to in the cloud is just the same Zeta that we have running locally. They can peer with each other. So we could take that app logic that I had and wire that up inside of Zeta running on Heroku, and we can start coordinating events happening between, or interactions happening between multiple physical devices. And we saw that query. Let me just go back to that in the app. To do that, it would look something like this from Detroit, where type equals LED. That's really the only difference. And then it creates sort of a virtual device representation for you locally, and you can interact with it just as you're interacting with it here in lines like 11 through 15. So. Hopefully we'll have some docs on that, some examples to show that, because I think that's a really super cool feature.
So I see you got your own instance of Zeta sitting on Heroku. Is there a public cloud Zeta server that you can link to and then just like have account access to deal with that? Or do you just need to go host your own Zeta somewhere?
Right now you just need to go host your own Zeta somewhere. I hope it's up to date, maybe it's not, but we did a Heroku button for this. Oh, wait, hold on. Come back here. It might be out of date in the package.json here. Yeah, that's I think we're on version 0.21, but we'll get that updated. And it's just as simple as coming here and clicking deploy to Heroku, and it'll deploy it right to Heroku for you, and then you can start hitting that. So. All right. Let me head back to this guy. All right, so a couple things we want to do moving forward, just to wrap this up. With streams, we have a producer-consumer problem. So, the producer, the device can send out, a new message every millisecond. Maybe I'm on a mobile app and I can't handle that. There are a few different ways we're aiming to solve that. Most of it comes out with really defining this WebSocket protocol with the object streams and what that looks like. And so, we're tentatively calling this reactive stream control protocol, but you could have consumer-controlled streams, right? So I could say, give me the next 20 events, give me the next 100 events, give me, the next 1,000,000 events, right? It would make it really high if I don't really care about the producer-consumer problem. It's going to run over WebSockets, of course, and it's going to be able to multiplex streams. So right now, there's a new WebSocket connection that goes out for each stream. Once this is in place, it's going to be just a single WebSocket connection, optionally more if you need them, but minimally just a single one that can subscribe to multiple streams and also do this flow control. It's going to have a URI scheme definition that's necessary. If you want to do something like hypermedia, you have to be able to represent that as a URI. And unfortunately for a lot of other protocols, we don't see a URI definition in place. And there's some de facto stuff that comes up. Like I think MQTT doesn't officially have one, but some MQTT clients will accept like an MQTT : / sort of string in there. It's really the new query string, isn't it? Not query string, connection string for databases. That's what I mean. And this will be supported in HTTP2 plus WebSockets going forward. So just like a few things you can do with streams, you can monitor those values over time. You can do distributed data processing, which is kind of a cool idea. Event sourcing, so kind of keep an audit log of everything that's happening to that particular object, and maybe keep a representation somewhere else. And of course, you can do batches. So we have kind of a lot on our to-do list, but here are a few things. We need to extract that hypermedia piece as its own thing. One interesting side effect of using this is that none of us want to use any other style API ever again, right? Every time we do, we say, well, we kind of need like a real-time update of this particular feature, and it just doesn't exist. Or we want to know what transitions are available, and they just don't exist. So it'd be cool for us to extract that to its own thing. So it can model more than just devices. All these protocols need to be specified in greater depth, and once we do that, we can start experimenting more with multiple languages and platforms, not just Node, right? Because it's just protocols talking here, right? Like the meaning is in the message, doesn't have to be baked into the code. So if you have any more questions about this, you can talk to me afterwards. Of course, you can hit me up on Twitter, LinkedIn, GitHub. These all had to be, except for the top one, URLs, because URLs are important to us. And another thing is that we are currently hiring on our team in Detroit. So if you're interested in this sort of thing, you have a passion for it, let me know. Thanks, guys.